Okay, so we're going to talk about chemical bonds. First, we're going to talk about some of the trends we see in the periodic table, and then move on to chemical bonds and relating the two, the trends and properties of molecules. When we talk about bonds, basically bonding between atoms will form our compounds, and this is just a crystal structure of vitamin C. We're going to look at the periodic trends first, and then we'll start working on our molecules. So when we talk about periodic trends, okay, we're able to predict chemical properties. One of the things that we're going to be looking at are metallic properties. So remember, what are some of the properties of metals? And some of the properties of metals include that they have that really beautiful metallic luster. They're malleable, they're ductile. So malleable, you can pound into very thin sheets. Ductile, you can actually pull metals and stretch them into wires. You pull wires from them. They're good conductors of heat and electricity. And they tend to lose electrons to form cations. Okay, nonmetals, they're not lustrous. They're brittle. Okay, when they're solids, they're brittle. Okay, and they're poor conductors. The other thing is, remember, for metals, they're primarily solids at room temperature. Okay, where, except for mercury, which is a liquid. But if you look at the nonmetals, most of them, we have some that are solids, but when they're solids, they're brittle. We have a lot that are gases. We have some that are liquids. Okay, so when you look at nonmetals, they're all three physical states at room temperature. And that's not the same for metals. Okay, and when they do have a reaction, they tend to gain electrons. Okay, and metalloid, remember we have some that touch that staircase. These ones have both properties, some of each side, some metal properties and some non-metal properties. Okay, so when we looked at the periodic table, metals are on the left side of the staircase, non-metals are on the right side of the staircase, and notice on this black staircase that the metalloids tend to touch that staircase. What's interesting is just keep in mind hydrogen is unique. It has some behaviors like the group 1A metals, but it is a non-metal. Okay. So what is the trend? So when you go down a group, the atomic radius increases. If you go left or right, it decreases. Now we're focusing on main group elements. Okay, because remember with the transition elements, it has a slightly different behavior because we're filling in the transition elements all of the core electrons. Well, here, let's just focus on our valence electrons. So why is it that my atomic radius decreases going from left to right? So remember, if you look at lithium, lithium has 3 protons, and fluorine has 9 protons. Remember, positive and negative charges attract. So if we're in the same shell, here's my electron, and I have a greater positive charge, so I have 3 protons and I have 9 protons here. then the attraction, if I have a stronger magnet, like a 9 protons here, then I have a much stronger attraction on that electron and it pulls it in slightly, whereas this one is weaker. So this nucleus pulls in my electrons more than the lithium nucleus pulling on those electrons, which is why lithium is larger than fluorine. So as you move left to right, you're going to see a decrease. Why do we see an increase going down? Because remember, this one is N equals 2. Okay. For sodium, it's N equals 3. So as you move down your shell, you're increasing because you have a larger shell. Oh, sorry about that. So just by the nature of increasing the shell, it's kind of like those embedded Russian dolls where you have a little one, and then to fit outside of that, you have to have a larger doll, and then a larger one, and then a larger one. So that would be like going from N equals 1 down to N equals 7. Okay, so down a group. Additional quantum levels, so they're farther from the nucleus. Okay, that's why the size increases. As you go across, okay, the N remains constant, but our atomic number, the number of proton, increases. So it has a stronger attraction with the electrons, and that's why it decreases. Okay, now let's talk about a property called ionization energy. And ionization energy is just the amount of energy to pull off an electron from your atom. Okay, so if I can pull off more than one, like for sodium it has up to 11 electrons, then the first electron is the first ionization energy. Pulling off the next electron is second. If you pull off a third, it's a third. And as you continue to pull off those electrons, it's harder to do. You need more energy, okay? Because already you have a cation and you're trying to make it more of a positive charge. So what's the trend? The trend is this. As I go down, it decreases. My ionization energy decreases. And as I go across, it increases. Okay, so why is this? Well, remember, as I go down a period, N increases. And as we spoke about the size of my atom, this is the atom at the top. Here's my nucleus. And this is my atom at the bottom. As I go down my row, so I'm increasing the number of shells, then the distance here is larger. And if the distance is larger, then the attractive interaction between my nucleus and my electron is weaker. Okay? And this goes back to this law called Coulomb's law. And that the energy of attraction is some constant times Q1, Q2 over R. Okay? You want these to be opposite charges for an attraction. So as R increases, from this equation, as R increases, the energy of attraction goes down. As Q1 and Q2 increase, not the ratio, but or Q2 increases, then my energy increases. Okay, so that's what we're learning from Coulomb's law. So as we go down, because it's not held so tightly in my atom, the amount of energy that's needed to pull this electron away is going to be lower. So IE is lower for this atom than this one, my original one. So as I pull this electron and put into a higher shell, a larger shell, my ionization energy goes down. And that's the trend we see. Likewise, remember how we were talking about R? So when you're in the same row and you're going across my period, then this is what happens. Here is the first element, but as you go across the row, remember my size decreases. So in this case, if R goes down, because it's on the bottom, it's going to do the opposite. E will go up. So when this happens, as I go across the same row, my ionization energy increases. Okay, so let me just go ahead and clear the screen. Okay, so we're talking about first ionization energies, all right? And so we explained the trend that we see, right? That as we move across each row, our ionization energy, the first ionization energy increases. But let me just tell you in a very coarse manner, I don't think that this is surprising to you. Yes, a new term. But don't forget, what do we know about metals, metalloids, and nonmetals? So remember, if we go back to our periodic table, metals are on the left. It's left of that staircase. As you move across the same period, you'll see the nonmetals are on the right. And what that means is that I went from metals being able to lose their electron easily to nonmetals, which gain electrons, which means they don't lose their electrons easily. Well, if I go left, loses electrons easily, to right, which means that they're nonmetals and don't like to lose their electrons, what do we see? The amount of energy that it takes to remove an electron increases. Okay, so we talked about the higher N is farther from the nucleus, so that's why it's easier to remove. If you, again, across a period, we see that it creates a greater interaction, right? The increase in positive nuclear charge and the reduction in size, so R decreases. It makes it difficult to remove the outer electrons. Okay, so what happens when we look at subsequent ionization energies? So if I look at removing the first from hydrogen and then the first from helium, okay, you can see that there's a huge increase. And then the second one. Now let's look at lithium. This is lower, because remember we said when we move down, it takes less energy. The ionization energy decreases. But look at this jump between lithium and just removing that first electron of lithium. Here, beryllium, it loses 2, right? So if you look at, here's the first electron, here's the second electron. Look at this jump right here. So why is there this sudden jump? Well, remember, hydrogen just has 1 electron. So you're going from hydrogen to, when I remove that dot, hydrogen plus. Okay, so it takes some energy to it. Lithium, to remove that first electron to lithium plus, okay, that wasn't so bad. But now I have to remove more electrons, and it's difficult to do. For beryllium, the first one, not so bad. The second one, not so bad, but now I've got to lose a third one, and here's a jump. So let's take a look and see what's going on. Okay, so what we find is this. Every time we remove an electron, okay, where you see this huge jump. So remember how we talked about valence electrons? Well, it turns out here, when we talk about valence electrons, what we're doing is we're removing the valence electrons, but now this jump is because we're removing all the core electrons, okay? So, all right, nonmetals have larger ionization energies. We're not surprised by that. Okay, so when we take a look at these electrons, the reason I want to get down to the configuration is this. For boron, if you see it, the huge jump was at 3 electrons. What that means is as I lose my first electron, I take it out of my 2p. Here's my electronic configuration. If I lose my second electron, minus E, then I lose another. If I do my third, then I just get helium. So what happens is this huge jump, the jump that we see in ionization energy, is when you start removing core electrons. Okay, because we are no longer, for boron, which is in row 2, my valence electrons, I have 3 of them, are in row 2, but I removed all of them. These are all core electrons. Okay, and that's why we see that jump. And that's why we see the jumps in ionization energy. Okay, so let's do Lewis dot structures now that we have an idea about our valence electrons and our core electrons. So remember, valence electrons, and we're going to focus now on our main group elements. Valence electrons are the outer electrons. Now, how can you tell? If you look at their electronic configuration, they have the highest principal quantum number. And you're going to sum all of them, okay? So if we look at, let's focus on carbon this time. So if you look at carbon, okay, so carbon looks like helium, 2s2, 2p2. So I have 4 valence electrons. And if you notice, it's in group 4A. So it turns out your group number here, the 4A, 5A, 6A, 7A, they actually tell you just by looking at it. Noble gases are 8A. It tells you the number of valence electrons. And that's why what happens with Lewis dot structures, a dot represents a valence electron. So for carbon, you would draw 4 dots. Okay, and don't line them up. Just imagine a box around the carbon and try to get an electron on each side of the box. Okay, if we drew oxygen, oxygen's in 6A. So for oxygen, with 6 valence electrons, 1, 2, 3, 4, 5, 6. Okay, so basically, when you draw your Lewis structures, make sure You make the dots large enough, it slows us down, unfortunately, but oftentimes the reason I insist on that, because it's hard to know what's an erased dot versus a true electron that you're trying to indicate. 2, notice how they drew it differently than I did. As long as you have your 6 valence electrons and you do attempt to put them 2 per side, then you're going to be fine. It doesn't matter what order. Okay, so for the germanium, like carbon, germanium is 4 valence electrons, so you're going to draw 4 dots around germanium. This works. Something a little cleaner. I like this one a little better. What happens if someone says, oh, I want to do it this way? Okay, so not ideal, but correct, right? Because I'm indicating I have my 4 valence electrons here. Okay, so if we look at iodine, iodine is in group 7A. It's a halogen. Because of that, we know it has 7 valence electrons. So when you draw iodine, you're going to have 7 dots around it. 1, 2, 3, 4, 5, 6, 7. This is the only one that has 7 electrons around it. Okay, so let's talk about the ionic bond. So remember, with the ionic bond, you transfer your electrons, so you get a cation and an anion. And then basically, you're going to get a charge attraction. So remember how we kept trying to make sure everything was neutral when we were done, because anions and cations have charges. So what happens is, for a cation, we talked about it loses an electron. For every electron it loses, it gets a positive charge. For an anion, for every electron it gains, it gets a negative charge. And metals tend to lose electrons, and nonmetals tend to gain electrons. So when we say, oh, metal, nonmetal, it's an ionic compound, it's because metals tend to lose electrons, become positive. Nonmetals tend to gain electrons and it becomes negative. Okay, so let's take a look at why they will lose their electrons. So the whole goal for these atoms is to try to completely fill the orbitals. Okay, so when they have completely full orbitals, they're going to be in what we call the noble gas configuration. All right, so helium, the 1s is full with 2 electrons. So if you look at hydrogen, hydrogen would either lose it so it's completely empty, or it will react to try to gain a second electron, okay, so it can completely fill it. Look how neon's completely full. Look at how argon's completely full. So because this is only a 1s, this requires 2 electrons to be full. But everything else, to fill the valence shell, you need 8 electrons. So that's our magic number of 8. So if we talked about trying to figure out what the charge is for a nonmetal, we said, oh, subtract 8. Okay, where did the 8 come from? It came from understanding our noble gas configuration. So here are all the noble gas configurations. Now, what happens, let's say, between sodium and chlorine? So sodium has 11 electrons and 1 valence. So the easiest way to form a noble gas configuration is to lose this electron and become like 1s, 2s2, 2p6. This would be neon. So sodium doesn't require a lot of energy to look like neon and lose that 3s1 electron. Now it's happy. What about chlorine? Chlorine, 1s2, 2s2, 2p6, right? 3s2, 3p5. All it needs is 1 more electron to look like a noble gas. So if it can add an electron, it'll look like 1s2, 2s2, 2p6, 3s2, 3p6. Okay, and that would be what? Argon. So when sodium reacts with chlorine, and I'm drawing my Lewis dots so you can see that these dots represent the valence electrons. That's a dot. What will happen is this electron will move to the chlorine to give me my sodium cation and my chloride anion. When it does this, this now looks like neon for the electronic configuration, and this will now look like argon. And that is actually why when we do these types of reactions, we get a transfer of electrons to form our ionic compounds. Okay, so let's move on. Okay, so it's easy to gain an electron here. So when we look at our reaction, when one loses and the other gains electrons, you form your ions, and they're held together by being oppositely charged. So again, how do we know this? So remember we talked about Coulomb's law? Now, no one said Coulomb's law was only applicable to electrons and to the nucleus. It just has to do with your charges. So if I have a charge of Q1 for my cation, Q2 for my anion, okay, then we can use again, invoke Coulomb's law and the attraction between charges to make them neutral. And that attraction, the larger these charges, the stronger the attraction. The closer they are, the stronger the attraction. Okay, so this is a noble gas configuration. That's a noble gas configuration. So notice when we have, if I say what's the electronic configuration of an ion for every cation, when you write the configuration, you're going to lose electrons for every positive charge. For an anion, you're going to gain electrons for every ionic charge. Okay, so now when we talk about our ionic structure, we know how the cations are formed and why. We know how the anions formed and why. So how is this different? How are ionic compounds different than molecular compounds? And let's just take a look at our lattice diagram. So from our lattice diagram, what we can see now is this. When we put them together, we can't tell which sodium and chloride ions belong to each other. We only know that they have to make it neutral. So this sodium ion right here, this red one right here, it can be paired with this chloride or that chloride. So that's why we actually call them formula units and not a molecule, but a formula unit. Just because we know that this is the lowest ratio of cations and anions that's neutral. Okay, so that's actually why we don't call it a molecule, because it can be paired with any of the chlorides surrounding it. Let's take a look at the sizes. Okay, well, if I lose an electron, then it's going to be smaller. So cations are always smaller than the neutral atom. What about anions? Well, anions, I gained an electron, so I'm putting more things in there. So it's going to expand because I have to put in something else. So what we find are anions are always larger than the respective neutral atom. Okay. All right. So this is just a table to show how different the sizes are. And they're talking about how dramatic the difference is. Don't forget, we dropped to get to this point. You're going from one shell less. So this is like looking at the size of the interior shell. Okay. Again, if you look at your radius, we're increasing. So by adding an electron here, or 2 electrons there, we show a fairly large increase in the size of our anion. Okay. So now when we talk about transfer of electrons, all we're saying is we're not restricted to just one. Okay. Magnesium loses 2 electrons. Chlorine only needs to add 1, but oxygen needs to add 2. Okay. So when you do form your ionic compounds, look at magnesium can give 2, so it gives 1 to one chlorine and the other one to the other chlorine, and that's how we end up with magnesium chloride. So that's just showing you how we can actually do this to form multiple ionic compounds that have multiple ions. Okay. Aluminum and oxygen. So with the aluminum, again, each aluminum can give 3 electrons. So 2 to this oxygen, 1 to that one. But now this oxygen does not have a noble gas configuration yet. So you need another aluminum to do it. Okay, so in the end, everything's neutral. So this is our formula unit for aluminum oxide. Okay. All right. Predicting the ionic compound formulas. Okay. So you just have to make sure they're neutral. And we've done this. All right. So basically, you look at barium and sulfur. Barium is in column 2A. So barium can become barium 2 plus. Okay. And it loses 2 electrons. The sulfur is in 6A. So sulfur wants to gain 2 electrons to become sulfide. Okay, so barium sulfide would therefore look like this, okay, to be neutral. But I think you could do this. So when you look at the periodic table, you would know what the charges were, and this is why. Because you're trying to get to the noble gas electronic configuration. Okay? All right. So let's move on. All right. When you look at group 1A, metals, the alkali metals, they all have one valence electron. So group 2A has 2 valence electrons. So that's why we know what the charge is going to be for our group, our main group metals. Likewise for our nonmetals, by looking at our column number, we can figure out how many electrons they'll need to have noble gas configuration. So phosphide, group 5A. So we know that the phosphide, that's phosphorus. So to get to 8A, this is my noble gas. It has noble gas configuration. If you look at, okay, when it gains 3 electrons. Likewise with potassium, it's group 1A. So we know it has 1 valence electron. So it has to lose that 1 to get its noble gas configuration. So how did the phosphide get 3 electrons? I needed 3 potassiums to give their electrons up to the phosphorus in order to form potassium phosphide. Okay. All right. What about magnesium nitride? Nitride means N3-, it's an anion magnesium. We know it's in 2A, so we know that's going to be a 2+. So if you do your crisscross, you'll get Mg3N2. Okay? So this is almost like a review of what we've been doing since the beginning of the semester. Now, covalent bonds, this bond is when it's sharing 2 electrons between 2 atoms, okay? And they're discrete units. So unlike when we looked at sodium chloride where we can see this huge lattice, if we have something like water, that's it. It's its discrete unit. So when we look at something like ice, it's a bunch of waters. They're discrete, and it has a different type of connection between 2 water molecules in ice. Okay, there's no formal covalent bond or ionic bond. Okay. So in here, my hydrogens have an electron each. But to get noble gas configuration, it needs to have 2 electrons to look like helium. So what they do instead is they share the electron pair. So each hydrogen thinks it has 2 electrons next to it. When that happens, basically it feels like it has a noble gas configuration. Okay. If you look at chlorine, when you overlap it, again, you have 2 electrons shared between the 2. So how do we draw these things? So when you have 2 electrons shared in a covalent bond, we use a line. Here, you can draw this out. But preferably, the bond here is shown as a line. What about the other electrons? So the other electrons, this is a bonding electrons, the other electrons these are called lone pair electrons, or you'll hear us refer to them as non-bonding electrons, or a non-bonding pair. Okay, So these are lone pair electrons or non-bonding electrons. They're not in the bond. Okay. And so lone pairs, this has 3 lone pairs. We're just referring to each pair. Or if you look at the individual electrons, then it's 6 lone pair electrons. Okay, so make sure you understand those terms. All right, so single bonds can be formed to get the noble gas. So hydrogen, fluorine, bromine, iodine. If we do a single bond, let me just H2I. This is what we would do to draw hydrogen. H line H. This is what we would do to draw fluorine. Draw our bond between the bromines. Okay. And these are called Lewis dot structures. Because what we're doing is we're drawing our valence electrons and the interactions because of the valence electrons in terms of bond formation. So if you recall, why spend so much time on valence electrons? Remember, they're responsible for a lot of the chemical reactions that we see. Okay, so we replace it with a line. Okay, now if you have 2 lines, this is called a double bond. Each line represents 2 electrons. So 4 electrons are shared here. And if I have 3 lines, this is called a triple bond. Okay. All right. So when we talk about a continuum, okay, so you're going to have bonds where it's shared equally. Then you're going to have bonds where it's an unequal sharing. It's still covalent. They're sharing it, but it's unequal. So if you had, let's say, $10 and you had to share it, okay? When it's a purely covalent character, is like each hydrogen here gets $5 each, equally shared. When it's polar covalent, then it's unequal. So someone like the hydrogen might get $2 and the chlorine would get something like $8. Okay? When it's purely ionic, all of my electrons are now, instead of most of the time being at the chlorine, it's always with the chlorine. So here, the sodium would get nothing and the chlorine would get all $10. So this is ionic. Okay? So we need to figure out how to determine if a bond is either covalent, purely covalent, polar covalent, or purely ionic. Okay, now is that the only 3 classifications? And the answer is no. It's a transition. So it might be that if one atom got $6 and the other atom got 4, it's close enough to basically a non-polar covalent that it would stay in this category. Okay, if you had it where it was 3 and 7, maybe it's still polar covalent. Maybe if it's 1 and 9, it's more polar covalent ionic. Okay, so if you look at the divisions, you can split them up differently than what's defined here. And so it's going to be a continuum between being purely covalent, or what we call non-polar covalent, up to polar covalent to purely ionic. Now when we say polar, what we mean is that it's a permanent dipole. It's like a permanent weak magnet. Okay? So we're not talking about charges or anything like when we're talking about ions. We're just saying that there's an unevenness to it. So this is like something that doesn't have any magnetic properties. This is a weak magnet, and this is a very strong magnet. Okay. All right. So how do we measure or determine if a bond is polar or not? And what we're going to use, what's often used, is this property called electronegativity. And what it is the measure of the ability of an atom to attract electrons in a covalent bond. So we're not talking about an overall charge. It's just that if I have a covalent bond between the hydrogen and chlorine, then if the chlorine is more electronegative than the hydrogen, it's going to pull those electrons, so the electrons spend more time with the chlorine. That's all we're saying. So the higher the electronegativity, the more that atom wants those electrons. Okay? So when that happens, and my electrons are more on the chlorine than on the hydrogen, we put a negative charge, but it's not an ion, so we don't put just a minus. We put a small Greek letter D. So it's like a D and then a minus. So this is a partial negative charge. And the D is called delta. Delta negative. Okay. That means if it's pulling the electron, spending more time with the chlorine than the hydrogen, then the hydrogen's slightly positive. So we put a delta positive of it. The other thing is you'll see us draw an arrow to represent the dipole moment. And the arrow starts where it's more positive, and it goes to where it's more electronegative. We talked already about ionization energy, and there are other properties that we actually measure for these atoms. And when we do that, Linus Pauling developed a relative scale. Okay, so if there are no units to it, okay, and it's a relative scale called electronegativities. The most electronegative element is fluorine, and the least is going to be like cesium. Okay, that's about a 0.9. So the higher it is, the stronger the atom's attracting the electrons. So what happens though is this. Suppose I look at chlorine. And I look at our hydrogen chloride again. Chlorine, we already said previously, has a high electronegativity. It's about 3. Okay? Why is it that this is nonpolar? And this is polar. If the electronegativity value for chlorine is so high. Because when we look at a bond, we're not so much interested in the absolute value for the electronegativity. We're looking at the difference in electronegativities. Okay, so in the difference in electronegativity, even if chlorine is high at 3, what's 3 minus 3? 0. That means that there's not this pull towards one atom only. Here, if hydrogen is, let's say, 2.1 and chlorine is 3, then that difference is 0.9. That's a large difference if you think that the total difference would be up to 4. So 0.9, because it's polar, this is too weak to stop chlorine from attracting those electrons. Okay, and that's why it's polar. So we're looking at differences in the electronegativity values. Okay, so what else do we have to consider? How do I subtract it? So remember the change in electronegativity. I'm going to write it up here so it's a little cleaner. Whenever we look at the change in electronegativity, we're always looking at the absolute value. Okay, so you say, what happens if I have a negative value? is really going to be, you're going to take the larger number and subtract the smaller number. Okay, just make sure you know which is your larger number. All right, so if 0.9 is a polar covalent and a 0 is a non-polar covalent, what are our scales for them? Okay, so here is the difference in our trends. So you can see fluorine, I mean, noble gases don't attract it, so there's really no value for it. But fluorine, oh, actually I was wrong. It was 0.7. Cesium and francium. Okay, these guys are 0.7, so that's the lowest in our electronegativity scale, and 4 at fluorine is the highest. Okay, so here's chlorine at 3. So I said, what about a chlorine-fluorine bond? Okay, 4 minus 3 gives us a difference of 1. So it's going to be polar. So typically, and there's a little bit of variance, but typically if we have a difference in electronegativity of 0, then it's purely covalent. Okay? Nonpolar and it's covalent. Our range, though, tends to be, if we say that it goes from 0 to 0.4, we're talking about nonpolar covalent. If we're talking about greater than 0.4 to less than 2, this is a polar covalent. And then we're saying that anything greater than 2, or equal to or greater than 2, is going to be ionic. If you take a look at some of these differences, though, you'll say, oh, what about magnesium, 1.2, and bromine, 2.5? Well, that's still, the difference there is about 1.3. So it's more on the polar covalent end, but it's closer to 2. So this is where, when we say the general rule is metal, non-metal, you'll see that when we look at some numbers, there's going to be some variance. But remember, this is a continuum. So, I would say still keep using the metal, non-metal for your ionic categorization. Okay, so when we look at the difference, we're talking about nonpolar. If it's greater than 2, okay, or equal to 2, it's ionic. If it's less than 2, then it's polar covalent. Okay, so if you look, covalent from 0, it is a graduation here, but we're just trying to break trends, so it's a little bit easier to classify. Okay, now non-polar bonds, very little difference. Okay, so we're just, remember again, we're looking at the differences in electronegativity. That's how we determine it. Okay, polar covalent, phosphorus, oxygen. Oxygen is a 3.5, just so you know. The phosphorus is 2.1. Okay, so that's why it's pulling towards the oxygen. What about if I said fluorine and nitrogen? Okay, so if I look at fluorine and nitrogen, then the difference in electronegativity is going to be equal to what? 4.0 minus 3. So that's going to be equal to 1.0. But fluorine is the 4, so it will go this way. And the fluorine is the delta minus, and then nitrogen is the delta plus. Okay? So, which is polar covalent? So, if we look at beryllium and fluorine, this is nonpolar. That's going to be 0. Nonpolar covalent. If you go back to our tables, you can see sodium and oxygen. This is metal, non-metal. This is ionic, right? Okay, we already know that from our examples we use hydrogen and chlorine to form hydrogen chloride as a polar covalent model, actually. And beryllium and fluorine, this is probably on the, let me see if I remember. Fluorine is 4. And let me look up beryllium for you. Beryllium, hang on 1 second. If you go to table 11.5 on page 233, okay. You'll see that beryllium is 1.5. So this is greater than 2. This is ionic. So the polar covalent is hydrogen and chlorine. Okay? All right, now, what about polar molecules? Okay, so a polar molecule is different than a polar bond. All right? What it means is that when we say a polar bond, it has a permanent dipole, it's like a weak magnet. A polar molecule is going to act like a weak magnet, but it's going to depend upon the geometry and the bonds. All right, so let's take a look here. If we look at a polar molecule, so I'm going to just write down the classifications here. So the molecules, polar and nonpolar. So if my bonds are nonpolar, then you'll have a nonpolar molecule. Okay? If my bonds are polar, it's going to depend on the geometry. You could have a nonpolar molecule. If I have polar bonds and the geometry is such that it allows it, I can have a polar molecule. So to have a polar molecule, I have to have polar bonds and the correct geometry. To have a nonpolar molecule, I have to have either nonpolar bonds, or if I have polar bonds, they cancel each other out. So the geometry is important. So let's take a look at this and then start talking about, what do you mean geometry? What's going on here? We're not doing any proofs. What we're doing is this. We're going to take carbon dioxide as our example. If I look at my carbon-oxygen bond, it's a polar bond. And if we draw the dipole moment, it'll look like that. So it has a direction and a value to it. So this has a direction wherever the bond is, and it has a value, a magnitude. Okay, so suppose I drew the bond, a bond this way. This bond has the same magnitude, but it's an opposite direction. So to me, it's like a tug of war. I have two equal strong men trying to pull the carbon, and it can't move because they're pulling equally. Because of that, these two cancel out, and so it's a nonpolar molecule. Okay, so we're talked about polar bonds, and now what we do is we use our understanding of whether the bonds are polar or nonpolar to determine if our molecule is polar or not. Okay, it's symmetric, so it is nonpolar. All right, so a permanent dipole, we were talking about molecules with permanent dipole, and we draw them as an arrow. Okay, so basically, well, that's what we've been doing already. Now let's talk about the Lewis structure so we can find out about the geometry. Okay, so in order to determine the geometry of our molecule, you'll need a structure, and then we'll talk about VSEPR to determine what that's going to be, the geometry is going to be. Okay, so we use VSEPR theory to figure it out, but before we can use VSEPR theory, we need to figure out how the bonds are. Okay, so here is the general strategy. When you're given your formula, your molecular formula, okay, or molecular polyatomic ion. When you're given your molecular formula, you're going to total the valence electrons. Okay. Now, if you have charges, remember, for every positive charge, you're going to subtract an electron. For every negative charge, you're going to add an electron. Okay? You're going to draw the arrangement. So how can you do this? Save hydrogen for last. Never put that in as a central atom. So when you do this, what you're going to do is you're going to put the least electronegative atom in the center. And then you're going to surround it by the other atoms. And you will draw a single bond from your surrounding atoms to your central atom. Okay, you're going to subtract the number so you know how many electrons you're going to be able to play with now. You're going to try to complete octets on the outside first, your outside atoms first. Okay, and then if you don't have enough electrons to complete the octet in the interior, you're going to form double or triple bonds. If you have extra, they're going to go on the center. So extra electrons go on central atom. Okay, so for instance, let's just talk about nitrogen trifluoride. So nitrogen is in group 5A, so I have 5 valence electrons. Okay, fluorine is a halogen. It's in column 7A, so it has 7 valence electrons. I have 3 of them, so it's 3 times 7. 21 plus 5, and it gives me 26 electrons to play with. Okay, now between nitrogen and fluorine, nitrogen has a lower electronegativity value. Fluorine is the highest at 4. So I draw my nitrogen in the center, I surround it by the fluorine, and then I'm going to draw my single bonds. Okay, so 2, 4, 6. That means now I have 20 electrons left to play with, right? So with my 20 electrons left, I have 1, 2, 3, 4, 5, 6. So I've completed the octet around this fluorine because 2, 4, 6, and it thinks this is it, 8. Okay, so we'll do the same to this fluorine, and we'll do the same to this fluorine. So now all my fluorines have octets. So, and how many electrons did I use? 2, 4, 6, 8, 10, 12, 14, 16, 18. So I used 18 electrons. So I have 2 electrons left. Okay, and this is 2, 4, 6, and it's going to go on my central atom. So that's what nitrogen trifluoride looks like. Okay, so, okay, we didn't talk about the shape, agreed on that. We're just right now trying to draw our Lewis structures, and then we'll talk about the shape. Okay, so let's get a little more practice. So here, the least electronegative atom, so carbon, I have hydrogen, I have oxygen, so carbon is in 4A, so 4. I have 2 hydrogens, that's 1A, so 2 times 1. And oxygen's in 6A plus 6. Okay, so that gives me 12 electrons to play with. Okay, we don't use the hydrogens for a central atom. It's more like caps because it can only do a single bond. There's nothing else. So between carbon and oxygen, carbon is my central atom because it's the least electronegative. Now let's go ahead and surround it. Draw my single bonds. All right, so of the 12, I use 6 electrons. for my bonds. So I have 6 left over. Okay. So if I do this and I say, okay, listen, I'm going to fill my octet 2, 4, 6. I use it. I have no more electrons. Well, that looks good, except for one problem. My oxygen has an octet. There's no octet here. Not good. Okay, so remember we said, well, if we ran out of electrons and we didn't fill our octet, we have to consider double or triple bonds. Okay. So what we're going to do is we're going to take these 2 electrons here, and I'm going to share it between the carbon and the oxygen. So let me redraw that. So here, I shared these 2 electrons. Didn't touch these guys. Didn't touch anything else. So all I did was redraw it with what I said I was going to share. Now, hydrogen's happy because it's got a single bond. This hydrogen's happy. It's got a single bond. Let me just redraw that so it looks prettier. Single bond. 2, 4, 6, 8. The carbon's happy because of that extra double bond, right? 2, 4, 6, 8. Now, all my atoms, so all octets completed. Okay. And hydrogen, again, hydrogens can only have 2 electrons. So they're happy as well. So that's what we do when we run low on electrons and we have to complete our octets. Then what we're going to do is consider double and triple bonds. Okay. What about carbon monoxide? So carbon monoxide, we have 4 carbons in 4A, so it has 4 valence electrons. Oxygen has 6, so we have 10 electrons. All right, so put in my carbon surrounded by my 1 atom oxygen, draw in my double, my bond, my single bond. So I use 2 electrons, so I have 8 electrons left. Okay, so say 1, 2, 3, 4, 5, 6, 7, 8. So 2, 4, 6, 8, 10. So now I used all my valence electrons. And what's wrong with this picture? I'll tell you what's wrong with this picture. Look at no octet. That's bad. We have to have our octet. So what we do then, since I don't have any more electrons, we're going to consider our double and triple bonds. So let's go ahead and share these electrons and put it right here. Is that good? Carbon has 2, 4, 6. Oxygen has 2, 4, 6, 8. But that's not good enough. Still, no octet. So let's do it again. Let's take this lone pair and share it. So if I do that, two, 4, 6, 8. This has an octet. 2, 4, 6, 8. So this one is actually the structure of carbon monoxide. Okay. What about if we look at something like nitrite? Okay. So if we look at nitrite, basically group 5A, so I have 5 electrons for nitrogen. oxygen 6A, and I have 2 of them. I have 2 times 6, and I have 1 because it's a negative charge. That gives me what? 12 plus 5 is 17, 18 electrons to play with. Okay, so when we do this, nitrogen is the least electronegative between nitrogen and oxygen, surrounded by my oxygens. Okay, draw my single bond. All right, so now, what do I have here? Now I have used up 4, so I have 14 electrons left that I can play with. So let's do our octet. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So now I use my 14. Okay, 0 electrons left. I use my 14. So let's check our octets. Oxygen has an octet. This oxygen has an octet. But look at nitrogen. 2, 4, 6. No octet here. Okay. I don't have any more electrons, so all we're going to do now is share. So let me share these 2 electrons between the 2, and I'll draw it down here. Okay, so 2, 4, 6, 8. This oxygen's good. Nitrogen has 2, 4, 6, 8. That's good. And this nitrogen has 2, 4, 6, 8. Good. So this is a good structure. But some of you might have thought, well, I don't want to do the green one. What happens if I did the purple way? And if you do the purple way, it would look like this. And this is an equally good structure. It turns out, if we're only looking at the difference of where that double bond is, they're called resonance forms. Okay, so you can get, there's a relationship between the two. And these are resonance structures. Okay, so when you put that in, okay, look at that. You can draw it this way or this way. That was the green, this was the purple. All right, and so when you have multiple structures where it's the same connections, in other words, it's an O and O. If you had OON, and you really avoid, by the way, having oxygens right next to each other as much as you can. You can't do that for hydrogen peroxide, but this is much more reasonable than having oxygen as your central atom and surrounding it by oxygen and nitrogen. So the same connection, O and O, but where those multiple bonds are, so changes, and that's why they're called resonance structures. And resonance structures are really formed. And what this means, though, is that limitations are not on the molecule side. The limitations are for us and the ability to draw a single molecule or a single ion in this case. So basically, both of these represent the same ion, but they're just drawn differently because of our limitations and the way we can draw these. Okay, let's take a look at carbonate. Okay, so if we look at carbonate, carbon has 4 valence electrons because it's in group 4A. Oxygen's in 6A, so it has 6 valence electrons, but I have 3 of them. And it has a charge of 2 minus, so I have to add 2 more electrons. So I get 24 valence electrons to work with. Okay, between carbon and oxygen, carbon is the least electronegative. I'm going to surround it by my oxygen. I'm going to draw my single bond. Okay, so I used 6 electrons, so I now have 18 left to play with. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So now, when we look at it, the oxygen has its octet, octet, octet. I used up my 18 electrons, so I don't have any more electrons left to play with. Okay, but my carbon has no octet. Okay, so like what we did for nitrite, we're going to take these 2 electrons and we're going to share it. And one thing I neglected to talk about in the previous slide, which I should do right now, is that when you have your ion, you put a square bracket around it, and put your charge here so we know it's an ion. Okay? So, carbonate, 2 minus. Now what's interesting though, is that I could also have done it from this oxygen. Notice from my parent structure that I'm getting good Lewis dot structures from. I'm copying anything I hadn't touched. Okay, so you get something like that. Okay, what happens if I didn't want to do that? Suppose I wanted to take these 2 electrons and put it here. Then you would get this for your structure. So it turns out all of these down here, I'm missing an octet, so not that one, but these 3 here are all good Lewis dot structures. The octet on oxygens and the carbons have been satisfied, and it turns out they're all resonance forms of each other. Okay? Okay, so that's what we did. They're all equivalent. These are good structures. I have octets on everything. These are resonance forms. Okay, so when we talk about, we're already talking about the polyatomics, we're already doing it. So when we talk about the polyatomic ions, now when you take a look at this, now you know why these act as a unit, because they are bonded to each other and behave as a single unit. Okay, and that's why you have 2 sodiums, because that has a charge of -2. All right, so let's go on to the geometry. Okay, we've been drawing Lewis dot structures, but what we haven't done is gone through and explained, well, we need the Lewis dot structures in order to help us on our way to determine is a molecule polar or nonpolar. So we need to understand how to predict the geometries. And so what we do is we use this called valence shell electron pair repulsion theory, or VSEPR theory. Okay, and what we're saying is that between our atoms, whether it's a single bond, double bond, or triple bond, this is called an electron group. Lone pairs can be an electron group as well. Okay, so when we say it's an electron group, all we're saying is that here is an area, a volume that has a high electron density, It has a negative charge to it because electrons are an overall kind of negativity to it. So they're going to repel other negative groups. And that's how we're going to predict, okay, the geometry. All right. So here, if we look at water, this is an electron group. That's an electron group. But don't forget, water has lone pairs. And so these lone pairs, those are electron group. And they're going to repel each other. They're going to push away as much as possible. It's kind of like if you ever play with balloons. If you take a balloon, let's say you take a balloon and you tie a knot here. Here's a balloon. If I take another balloon and I tie a knot to it and they're connected, then they're going to try to be as far apart from each other as possible. So if you play with balloons, you will get 2 balloons will be 180 degrees from each other. Okay, it'll look like carbon dioxide. 3 balloons, okay, will look more like it'll be flat but as far away from each other. And 4 balloons will take on something like the methane structure. It's called tetrahedral. Okay, so where does water go? It's V-shaped. It's actually what we call a bend. So let's talk about where that will fit in. So we have 2 things. We have an electron group geometry and we have the molecular geometry. So the electron group geometry, you're looking at electron groups, whether they're bonds with atoms attached or lone pairs. Okay, the molecular geometry is a subset of your electron group, and you're looking at the atoms only. So if I have 2 electron groups only, he's calling them electron pairs, but I find that to be confusing. So one here and one here. The furthest they can get away from each other and yet still be attached to the beryllium is if they are in a linear orientation. Okay? And this angle from here to here is 180 degrees. Okay? So if we look at a molecule that has 1, 2, 3 electron groups, then the furthest apart that they can be is going to be 120 degrees. It's going to be flat, or what we call planar. And if you look, it's 3-sided. So this is called trigonal planar. And the bond angle here is going to be 120 degrees. What happens when we have 4 electron groups? When you have 4 electron groups, if it were flat, the maximum angle is 90. But molecules are 3-dimensional. So what's going to happen is because they're 3-dimensional, one's going to pop out of the plane of the paper and one's going to go back into the plane of the paper. And when that happens, it forms a 4-sided, so tetrahedron. So this is the tetrahedral geometry. And when it's tetrahedral, your bond angle actually is 109.5 degrees. So it's not 90. Once it becomes 3-dimensional, I can make that angle larger. And since they're repelling each other, you want to go to the largest possible angle. And so it's going to be 109.5, and that's tetrahedral. All right. Now let's talk a little bit about lone pairs and molecular geometries. Okay. So when we have lone pairs are also an electron group. Okay. But they're fatter and squatter, and so they repel and push down on our bonds. Okay. So when you look at this, I have 1, 2, 3 on the nitrogen. I have 1, 2, 3, 4 electron groups. So my electron group geometry is tetrahedral. But if I look at my molecular geometry, it's different because when I look at molecular geometry, I'm looking at the orientation of the atoms. Okay, and if I look at the atoms here, my lone pair is pushing down on all these bonds. So my bond angle is actually less than 109.5. For ammonia, it's about 170 degrees. But now if I look at this, this actually looks like a three-based pyramid. So it's like a trigonal pyramidal geometry. Okay? And that's because I have one lone pair on my central atom. Okay? So if I have 4 electron groups, so one is a lone pair, it's actually trigonal pyramidal. Okay? So this fat squat, it almost looks like a turtle with 3 legs. Okay? It's a fat squat pyramid right there because this top one is a lone pair. Now when water has 2 lone pairs, okay? So the electron pair geometry is tetrahedral. I have 1, 2, 3, 4 electron groups. But because I have 2 lone pairs, and we're looking at the molecular geometry, when you draw this, this is just bent. Okay, hydrogen, oxygen, hydrogen, which is how we typically draw our water. Notice our lone pairs are not in the plane of the page, but going back and coming out. Okay, but for molecular geometry with 2 lone pairs, it's bent. Okay. Now, we need to do one more. Okay. We start here, and then we'll go through. What about if you had trigonal planar? So, electron group geometry. So if we look at something like our nitrate ion, okay, it has 1, 2, 3 electron groups, so it's trigonal planar. And that's both for my electron group geometry, and since everything's bonded, it's trigonal planar for my molecular geometry. If we look at, we drew this earlier, nitrite. So you can see my electrons here. This is my nitrite. Okay, I have 1, 2, 3 electron groups. So it's trigonal planar for its electron group geometry. But I have 1 lone pair on the nitrogen. And when I look at my 1 lone pair, if we do molecular geometry, again, it's called bent. Okay, so for trigonal planar, it's either trigonal planar for the trigonal planar electron group geometry, either it's trigonal planar for the molecular geometry with no lone pairs. If I have 1 lone pair, it's going to be bent. Okay, now determining molecular shape. So now we have all these geometries that we need to consider. And we're going to draw the Lewis structure. You're going to look at the electron pairs. You're going to try to get the geometry to minimize okay, repulsion. So we're looking at VSEPR, okay. So when you draw it, you're going to draw this in the appropriate shape, okay, to represent what we know from VSEPR, okay. So for formaldehyde, if we draw, remember it's 4 plus 2 plus 6, and we've done this example, okay. So when we draw it, notice how we try to make it look at, when we draw the structure, after you draw the structure, once you know its geometry, you're going to draw this in the appropriate geometry. Now I have 1, 2, 3 electron groups around carbon. So the electron group is trigonal. Remember, that means 3. It's 3-sided. Planar. Okay. On the carbon, I have no lone pair, so the molecular geometry as well is trigonal planar. So it's going to be B. Okay. So draw your Lewis structure. Then when we do this, we try to rearrange it to make sure it has the appropriate geometry. Okay. What about for phosphine? So when we draw phosphine, we have 5 electrons plus 3 times 1. I have 8 electrons to work with. So between the phosphorus and the hydrogen, we don't use a hydrogen for a central atom. Surrounded by the hydrogens, draw our bonds here. So 2, 4, 6, and I have 8, so these two go right here. Now, just so you're aware, this one is drawn flat, but I have 4 electron groups. So we know the electron group geometry is tetrahedral. And tetrahedral is 3-dimensional. So how do we convey the 3-dimensionality to it? And what we're going to talk about right now is we're going to use solid and dash wedge bonds. Okay, so when you have a wedge bond, if it's solid, it means, I'll put an X here and a Y. Y is coming out of the plane. It's coming out of the plane of the paper towards you. Okay. If it's dashed, if it's dashed, that means Y is going away from you, is going away from you. And if it's a straight line, it's in the plane of the paper. So now that we have the general format for phosphine, let's go ahead and talk about the molecular geometry. So we know that the electron group geometry is tetrahedral, but I have 1 lone pair, which means that my molecular geometry is trigonal pyramidal. Is that squat pyramid? So how do we do this? What we're going to do is when you draw this, then go ahead and draw your tetrahedral, put your lone pair on the top. One line here is in the plane of the paper. And then I don't want to get so far down. I want to make it so it's pretty clear. I have one bond coming out towards you and one bond going away from you. So this is how you would draw your 3D trigonal pyramidal. And this is going to be trigonal pyramidal. Okay? This is flat. It's just your Lewis dot, so you know all the connections. And then when you actually draw your geometry, you're going to use your dashed and wedge bonds to indicate three-dimensionality. Okay? So here is what it looks like. So it might not be something you're going to draw right off the top as soon as you get it done. You might have to do your Lewis structure flat first and then redraw it in the appropriate geometry. Okay? So after that, now we can look at your bonding electrons. What about carbon tetrachloride? So if we do carbon tetrachloride, this is 4 plus 4 times 7. So we have 32 electrons. Okay? So if we draw our Lewis dot structure, carbon's the least electronegative, surround it. Let me put a little space here. Okay? Carbon surrounded by my chlorines. Draw my bond to connect them all. 2, 4, 6, 8. So I used 8. So now I have 24 electrons left. Okay. So 1, 2, 3, 4. Just 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Okay, so now I used up all my 24. I have nothing left. Let's check my octet rule. So carbon has 2, 4, 6, 8. Carbon's good. Each chlorine has 2, 4, 6, 8. 2, 4, 6, 8. 2, 4, 6, 8, 2, 4, 6, 8. Everything has an octet. So my octet satisfied. This is a good structure. Now, we need to think about the geometry now that we have a good structure to work with. Carbon has 4 electron groups on carbon. So the electron group geometry is tetrahedral. Okay, so do I have any lone pairs? So the no lone pairs, everything's bonds. So my molecular geometry is also tetrahedral. Okay, so when we draw this, carbon in the center, and remember how I drew my lone pair here. Here's one of the bonds. Tetrahedral, so you're going to use your solid wedge bond. You're going to use a dash wedge bond. Okay. This chlorine is going away from you into the paper. This chlorine is here coming out towards you. This chlorine is in the paper. And this chlorine is in the paper. Okay, and you're going to try to draw it so that this bond angle right here is 109.5. So make sure you don't draw it so it's 90 degrees. make it larger than that. So we know the molecular geometry is tetrahedral. Okay. So again, after we drew the Lewis structure, made sure it was good, we redrew it where we had our solid wedge bond and our gas wedge bond to show the 3D to it. Okay. All right. So, and then we give the geometry. What about, is it polar or non-polar? So this is what's going to happen. When you look at your geometries, it turns out if your geometry, as in this case, is symmetrical, and all your dipole moments are of equal magnitude. Okay, and the dipole moment is for the bond, so you're going to have it in the direction of the bond. They're going to cancel out. So it turns out that even though the bond is polar, they cancel out. So this is a non-polar molecule. Okay. So it's due to the polar bonds are arranged symmetrically. Okay. So it's non-polar. All right. So you can see how they're arranged symmetrically here. So what we have to do though, when we take a look at our molecules, you're going to be now drawing the Lewis structure, getting the molecular shape, and then determining if our molecule is polar or non-polar based on our understanding of polar bonds from electronegativity. So what's a molecular geometry for carbon dioxide? When we draw this, I only have 2 electron groups. So both the electron group geometry and the molecular geometry is linear. Okay. Is it polar? No, the bonds are polar, but what we saw before, it's symmetrical in geometry, so it's a non-polar molecule. Non-polar linear molecule. Okay. So linear, draw it out. Okay. Now let's practice here. So if we practice, we're going to draw the structures, define what the electron group geometry is, and then the molecular geometry, and then if it's polar or non-polar. So let's do 1. Oxygen, 6. Fluorine has 7, so 2 times 7, 14. That gives us 20 electrons or so to work with. Okay, so put oxygen, between oxygen and fluorine, believe it or not, oxygen is the less electronegative atom, so I'll put oxygen here, surrounded by my fluorine. Draw my bonds. So now I have 2, 4, so I used 4. So I have, what, 16 left? Okay. So let's do our octets. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So I used 12. I have 4 left, so they're going to go on the central atom. So 1, 2, 3, 4. So I have no more electrons left. Okay. So let's take a look. 2, 4, 6, 8. 2, 4, 6, 8. 2, 4, 6, 8. All my octets are used, so this is a good Lewis dot. But now we need to talk about our geometry, right? So when you look, I have 1, 2, 3, 4 electron groups. So my electron group geometry
is tetrahedral. However, I have 2 lone pairs. So it's going to look a lot like water. So the molecular geometry is bent. Okay, so let me draw it over here on the left. I have my oxygen, draw my fluorine, draw my fluorine. So this is how you would draw oxygen difluoride bent. Okay, the angle is going to be less than 109.5 because I have 2 lone pairs sitting on it. And now we have this. So we did the Lewis dot. We did a good one. Then we have the molecular structure. So we know it's bent. And we redrew it with the molecular structure. And now, is it polar or non-polar? So I'm going to put in light green. Fluorine is electronegative and it pulls this way. And the fluorine here is electronegative and it pulls that way. There's no arrow that I'm drawing that's pulling up to cancel it out. So both of them are pulling down in that orientation. So because my polar bonds, the dipole moments are not canceled out, this is a polar molecule. Okay, let's try hydrogen iodide. Okay, just erase this here. All right, let's do number 2. Hydrogen iodide. Okay, so if we look at hydrogen iodide, I have 1 from my hydrogen, 4 from my carbon, 5 from my nitrogen, so I'm going to have it as 10 electrons to play with. Okay, now when we do this, we're not going to use hydrogen as a central atom. So between carbon and nitrogen, carbon's the least electronegative. So I'm going to put carbon here. I'm going to surround it by my other atoms. You're going to draw a single bond to each. So now I used up 4 electrons. I have 6 electrons to play with. Okay, so we have 6 electrons to play with. Hydrogen's fine because hydrogen can only take 2. So nitrogen needs an octet. So 1, 2, 3, 4, 5, 6. So I used up my 6 electrons. But there's a problem. My carbon doesn't have an octet. So when that happens and I don't have any more electrons to play with, what I'm going to do is I'm going to start sharing. I have to start thinking about double and triple bonds. So if I took those 2 electrons and I share it between the carbon and the hydrogen, I get my hydrogen carbon with a double bond to the nitrogen. And I'll just redraw my lone pairs because I didn't do anything to those 2. Okay, again, no octet. So now I have to again share. So 2 on hydrogen, hydrogen's good. But now look at carbon, 2, 4, 6, 8. So carbon is now good. Nitrogen still has 2, 4, 6, 8. So this is a good Lewis dot structure. Now we can start. Okay, so some of the work that we're doing ahead of time is necessary so we can actually start doing the molecular structure and determining if the molecule is polar or non-polar. Okay, so now that we have a good structure, how many electron groups do we have about my central atom? And it turns out I have 1, 2. have 2 electron groups. Okay, so remember we said it didn't matter if it was single bond, double bond, triple bond, or lone pair. It's an electron group. I have 2, so both the electron group geometry and my molecular geometry is linear. And we drew it linear, so I don't need to redraw it. Okay, so this is good. Now, what happens when we consider, is the molecule polar or nonpolar? So hydrogen to carbon, this is a nonpolar covalent bond because the difference is 0.4. If we look at carbon to nitrogen, it turns out that the difference is 0.5. So carbon to nitrogen is considered a polar bond. Okay. Well, I don't have anything to cancel it out. It's linear like carbon dioxide. So if I did have a vector here, but the magnitude isn't there, this is essentially not strong enough to be considered polar. So now, because I have an arrow, it's not canceled out. It is a polar molecule. All right. So, and I think we already did carbon tetrachloride, in our previous example. So I want you to go through and assess the nitrate ion. Okay. Draw your Lewis dot structure, then draw the molecular structure and tell me what that is, and then determine if the molecule is polar, or in this case, the anion is polar or nonpolar. Meaning, do I have a dipole moment? That's what we mean by polar or nonpolar. This has a charge to it, but that doesn't tell you it's polar or nonpolar. Okay? All right, so breakout session 10, you're just going to do some more practices like for experiment 11. You're going to also look at your trends for your radius. And when we do our electronic configurations, okay, since for vanadium, you're losing 2 electrons for vanadium. Okay, you're going to lose it from your outermost shell. So you're going to lose it from, you're going to lose 2 valence. So remember, it's your valence electrons you're removing. So remember to remove the electrons from your outermost shell when you're removing your electrons. Okay? All right. I hope this was a good explanation for how to look at trends, periodic table trends, and how to draw your structures.